8 billion tons is the total volume of plastic waste currently transforming the global oceans into a colossal floating graveyard. Why does this material pose such a terminal threat to the marine ecosystem? It would seem that the vastness of the water could absorb any impact, but in reality, the chemical stability of polymers ensures they remain intact for centuries, silently poisoning the entire food chain. This global disaster represents a hidden mineral deposit of resources waiting for extraction. The force of hydraulic claws and the precision of laser systems convert the most contaminated debris from the Pacific into a sterile and perfect industrial product. The battle for planetary recovery initiates in the open sea, one of the most hostile environments imaginable, where nature allows no margin for error. Over 20 million tons of debris flow into the world's waters every single year. One can notice how approximately 80% of this massive volume consists entirely of plastic. This material is so durable that it resists degradation, capable of enduring hundreds of years beneath the surface while accumulating in massive garbage patches. But this is just the beginning. Engineers have designed specialized vessels that function as industrial predators to confront this unending tide. These machines operate in critical zones such as the North Pacific Gyre. Each ship carries two massive hydraulic mechanical arms that extend outward from the hull. The equipment gradually sweeps the water surface in a broad fan-shaped pattern. It is visible how steel nets and stainless steel conveyors swallow plastic bottles and discarded fishing nets in a synchronized movement of force. A single cleaning operation lasts between 8 and 10 hours without interruption. The process is only gaining momentum. One vessel can recover up to 10 tons of a toxic mixture of marine waste during a single deployment. But the war against plastic is not limited to the deep ocean. Before reaching the sea, enormous quantities of waste become trapped in rivers and canals, creating dense barriers that suffocate the natural flow of water. Here, the tactical approach changes significantly. Heavy excavators mounted on specialized chassis enter the scene, equipped with steel clamshell buckets weighing exactly 1,000 pounds each. It seems simple to just lift debris from the water, but in reality, the weight of water-soaked waste requires immense mechanical power. These machines dive deep, tearing through the surface to extract heavy mixtures of bags, branches, and discarded tires. One can notice the ladle rising with the hiss of hydraulics and a slow tilt of the boom. Every individual lift removes up to 1,000 pounds of debris from the channel in a single movement. The process moves to the next level. The power of hydraulics allows a single team to clear a river segment, measuring hundreds of feet in length in just a few hours. This industrial method is 10 times faster than any manual effort. The roar of the engines continues as the mechanical arms repeat their cycle. The debris is moved from the water to the transport beds without pause. This material is then prepared for the next stage of the reclamation sequence. The collected waste enters a phase of stabilization and transport toward the processing facilities. Each ton of recovered plastic represents a reduction in the pressure exerted on the marine environment. From here, the transformation moves to the next phase of processing. 5 tons of unwanted material are accumulated by a single compact vessel during one 8-hour shift of continuous operation. Why is this specific volume of waste gathered before returning to the coastline? The efficiency of the logistics chain depends on maximizing the cargo capacity of these specialized boats. But in reality, any delay in transport would allow the organic components to begin decomposing prematurely. Specialized vessels, engineered exclusively for the transport of this environmental burden, ferry the debris back towards solid ground. The process is only gaining momentum. One can notice the specialized transport vessels signaling the transition from marine chaos to industrial order as they approach the docks. Hydraulic conveyors activate with a steady rhythmic pulse to discharge the towering heap of refuse into the reception zone of the processing facility. The equipment gradually moves the saturated mass from the hull to the concrete staging area. It is visible how the mixture consists of a confused and soiled conglomerate of plastics, metals, timber, seaweeds, and thick organic silt. At first glance, the pile appears as total chaos, yet the immediate objective is to distinguish between hazardous components and materials that retain industrial value. But this is just the beginning. professional sorters execute a rapid visual inspection of the incoming flow to safeguard the integrity of the downstream systems. The workers manually extract massive objects such as heavy steel netting or discarded tires that possess the structural density to destroy sensitive machinery. Once these obstructions are removed, the remaining material is mechanically pushed toward a high-capacity industrial sorting system. Everything only gets more complicated. 1,000 millimeters or more is often the diameter of the rotating components within the heart of this mechanical stage. The central element is the trommel screen, a massive rotating cylinder that functions as a heavy-duty mechanical sieve for the incoming waste stream. While the cylinder rotates with a constant metallic roar, it utilizes centrifugal force and gravity to categorize the debris strictly by physical dimensions. One can notice how the equipment separates the stream into distinct fractions, isolating sand, shells, and smaller particles from the larger bulk. The material continues its movement through the sorting circuit as the primary classification concludes. 160 to 180 degrees Fahrenheit is the temperature range where chemical purification begins for the recovered material. Why must the plastic undergo such an intense thermal and chemical bombardment instead of a simple rinse? At first glance, the material seems ready for processing after the initial sorting. But in reality, microscopic contaminants like salt, oil, and bacteria from years in the ocean would compromise the structural integrity of the recycled product. This creates a mandatory requirement for surgical cleanliness before the transformation can continue. Smaller fragments descend through specialized openings, while larger containers and packaging remain on the elevated conveyor to continue their trajectory. One can notice how the residual stream, now consisting primarily of various polymers and nylon, moves toward a manual sorting station. The equipment gradually feeds the belt where human operators identify and isolate specific categories with high precision. But this is just the beginning. Plastic is systematically separated from remnants of metal and glass to prepare for a radical purification sequence. It is visible how the raw material is propelled into mechanical washing tanks equipped with heavy-duty rotating shafts. These components rotate ceaselessly to generate a violent, turbulent flow that mimics an industrial-scale washing cycle. The process is only gaining momentum. The high-speed friction of the echelons effectively scrapes surface debris and organic matter from the polymer fragments. This mechanical action alone is insufficient for deep cleaning, so the water temperature rises to between 160 and 180 degrees Fahrenheit. Chemical cleaning agents are introduced into the heated solution to dissolve stubborn oils and neutralize salt deposits. For a duration of 15 to 30 minutes, the material remains submerged in this high-energy thermal environment. Everything only gets more complicated. The camera glides along the transition point where the heated plastic enters a high-speed drum washer. Jets of high-pressure water strike the material to dislodge any remaining grains of sand or microscopic particles. It only looks obvious that the material is now uniform, but in reality, different polymer types are still intermingled. It gets more complex further on. The separation of these distinct plastic types is achieved through the physical laws of density in specialized flotation tanks. Polyethylene terephthalate, commonly known as PET, possesses a higher density and sinks to the bottom of the tank. Meanwhile, lighter plastic variants remain on the surface, allowing for an automated separation without any manual intervention. One can notice how the different layers form naturally within the liquid medium. 4 stages of drying and deodorization follow the density separation to ensure the material is chemically stable. Systems utilize hot air at 170 degrees Fahrenheit to remove all moisture from the purified flakes. Simultaneously, ozone injection systems neutralize any lingering organic odors associated with the maritime environment. The process is only gaining momentum. The distinct scent of the ocean and swamp is completely eliminated through this oxidation phase. What remains are pure plastic fragments, stripped of their past and prepared for structural destruction. The material is now ready to move to the next processing phase without haste. 2,000 to 3,000 pounds of plastic are consumed every 60 minutes during one of the most aggressive and precise phases of the entire industrial cycle. Why must these containers be subjected to such violent destruction? At first glance, the clean bottles seem ready for processing, but in reality, their irregular shapes make thermal treatment impossible. The material is fed into a high-speed granulator, where the technical requirements for uniformity take precedence over the preservation of the original form. Centenas of alloy steel blades rotate at several thousand revolutions per minute within the reinforced crushing chamber. One can notice how the equipment gradually reduces the bulky containers into minuscule fragments known as flakes. The process is only gaining momentum. This mechanical reduction happens with a continuous deafening sound as the metal edges slice through the polymer structures. Smaller particles melt significantly faster during subsequent thermal stages. It is visible how the mountain of volume transforms into a steady stream of plastic confetti in a matter of minutes. By reducing the surface area of the raw material, the plant saves up to 40% of energy during the later phases of the production line. But even after multiple washing cycles, microscopic intruders can still compromise the integrity of the batch. It only looks obvious that the material is pure, but in reality, a single splinter of wood or a fragment of incorrectly colored plastic acts as a contaminant. Technology takes command at this junction to prevent the ruin of the final product. Optical sensors and high-frequency lasers examine every individual flake with millisecond response times. Everything only gets more complicated as the speed increases. The computer detects impurities such as microscopic metal shards or off-color polymers through constant scanning. Therefore, the system triggers a compressed air valve that fires with the precision of a calculated strike. This focused jet of air removes the defective particle from the main flow, while the camera glides along the remaining stream of purified material. A single sorting unit processes more than 1,000 particles every second. Maintaining a precision rate of over 95% ensures the transition from chaotic raw material to an ordered technical resource. The process is only gaining momentum. From here, the approved flakes move toward a massive extrusion unit for the final transformation. One can notice how the solid plastic begins to yield as the internal temperature rises to 520 degrees Fahrenheit. At this extreme thermal threshold, the solid flakes surrender their structure and liquefy into a homogeneous melt. The material is ready to move to the next processing phase without haste. 480 degrees Fahrenheit is the precise temperature required to initiate the next phase of structural transformation. Within the processing chamber, the polymer mass softens until it reaches the consistency of a viscous, glowing paste. A massive rotating screw assembly drives this plastic lava forward with constant mechanical pressure, forcing the material through a series of ultra-fine metal screens. One can notice how these microscopic meshes capture any lingering contaminants that may have evaded the earlier laser sorting systems. This purified flow of plastic is then submerged and cut underwater, instantly solidifying into millions of individual granules known as pellets. Why is the creation of these tiny granules necessary for the manufacturing cycle? The pellets represent the fundamental raw material for new production, but they do not yet resemble the final container. The granules are subsequently reheated to 480 degrees and forced into precision-machined steel molds via high-pressure injection. The resulting object is not a full-sized bottle, but a preform. This component resembles a thick-walled test tube, possessing a compact profile that already features the finalized screw threads for a cap. It is visible how the robotic manipulators organize these units for transport. This dense form is technically efficient, as it allows for the shipment of millions of future bottles within a confined logistical space. The process is only gaining momentum. Preforms are engineered for high durability, designed specifically to withstand the mechanical stresses of the final metamorphosis. At first glance, the small plastic tube seems static and rigid, but in reality, it contains the exact volume of material required for a 2-liter vessel. Everything only gets more complicated as the preforms undergo a second heating cycle until they become soft and pliable, reaching a state similar to hot rubber. They are fed into the blow molding machinery where high-pressure compressed air is violently injected into the heated core of the tube. The plastic stretches instantly under the pneumatic force, expanding between 4 and 5 times its original dimensions until it presses firmly against the chilled walls of the metal mold. One can notice the rapid dissipation of heat as the polymer stabilizes. In a matter of mere seconds, the small tube has transitioned into a structurally sound, perfect bottle. Modern production lines discharge thousands of these units in a fraction of a minute, maintaining a defect rate that is practically non-existent. But high velocity does not equate to a lack of precision in the engineering flow. As the bottle exits the mold, it remains thermally sensitive and vulnerable to deformation. The camera glides along the conveyor as the containers move toward the final inspection sensors. The transformation of the raw polymer concludes this phase, opening the road to the final quality assessment and packaging. 100% of the surface area of each container is immediately subjected to the influence of a fast-cooling chamber to solidify its geometry and lock its molecular structure. Why is this sudden thermal drop necessary for the final product? The rapid reduction in temperature prevents the polymer from warping or losing its intended shape, ensuring that the dimensions remain stable for the rigorous inspections that follow. At first glance, the container looks finished, but in reality, it must still survive a battery of high-precision electronic evaluations. High-resolution lasers and specialized optical cameras scan the surface of the bottle every single millimeter with absolute persistence. They search for micro-scratches, microscopic air bubbles trapped in the polymer, or any minute imperfection regarding the consistency of the wall thickness. One can notice how the equipment gradually identifies and rejects units that deviate from the strict engineering tolerances. But this is just the beginning. For containers intended to hold beverages, additional chemical sensors and laboratory tests ensure that there are no harmful residues or contaminants remaining from the recycling process. The process is only gaining momentum as the volume of approved units grows. Only the specific bottles that successfully pass through this military-grade scrutiny are eventually handled by high-speed robotic systems. These automated manipulators organize thousands of individual units with millimetric precision, stacking them into dense, stable pallets that are ready for immediate shipping. It is visible how the mechanical arms move with a constant fluid rhythm to prepare the cargo. Transition to the next level. 8 billion tons of discarded material and insulators were the starting point of this industrial journey, representing a massive weight of waste suffocating the delicate ecosystems of the world's oceans. It looked like the end of the line for these materials, but now, infinite rows of transparent, sterile, and structurally perfect bottles stand ready to return to the global supply chain. What was once classified as toxic debris floating in the Pacific Ocean has been systematically purified by the combined forces of thermal energy, purified water, and concentrated laser light. The material has been reborn as a high-value industrial resource through a series of complex mechanical and chemical transformations. This facility does not merely manufacture plastic products. It generates the physical proof that engineering and persistent human will can effectively close the production cycle. It proves that major environmental errors can be recalculated and converted into sustainable industrial solutions. The equipment continues to operate, ensuring that the ocean breathes a little better as the volume of recycled material increases. In the context of modern heavy industry, nothing is lost and everything is transformed into a new state of utility. This concludes one of the most critical stages of the material's life cycle, where waste is redefined as a primary asset. If California were an independent country, it would currently rank as the 5th largest economy in the entire world. $3.5 trillion represents the immense economic power of a territory that now faces its most severe environmental crisis in over 1,200 years. This geographic giant, built on a foundation of concrete and massive agricultural production, is struggling against a drought that has systematically depleted its primary water sources. Why would engineers attempt the seemingly impossible task of converting the vast Pacific Ocean into a source of potable drinking water? The project represents a desperate response to rivers that have stopped flowing and mountain ranges where the winter snowpack has virtually disappeared. Advanced technology and extreme hydraulic pressure are now the only tools left to reverse a natural decline that threatens the stability of an entire state. California functions as the essential agricultural engine for the United States. One can notice how the landscape transitions from coastal regions to fertile valleys that produce 1/3 of all American vegetables. 2/3 of the country's nuts and fruits are also cultivated in these expansive fields. But this is just the beginning of the challenge. At first glance, the state appears to be a green miracle, but in reality, this productivity demands 80% of all water consumed within its borders. This is a debt that the local ecosystem can no longer sustain. It only looks obvious that the land will remain productive, But the natural cycles that once supported this growth have reached a point of total collapse. The Sierra Nevada mountain range historically functioned as a natural reservoir by accumulating snow in winter and releasing fresh water during the summer months. Today, that cycle is broken as the snowpack has decreased to unprecedented levels. Vital reservoirs, including Shasta and Oroville, have plummeted to critical storage capacities of only 40%. One can notice how the fertile earth begins to crack and transform into clouds of red dust under the relentless sun. The process of desertification is gaining momentum. Humans could no longer rely on the arrival of seasonal rains to replenish these drying basins. The strategic solution required looking toward the western horizon at the millions of gigatons of saltwater contained in the Pacific Ocean. But how can a saline ocean be moved and processed effectively onto the mainland? The answer is found in an industrial artery system constructed from specialized carbon steel and high-density polyethylene. Engineers have designed massive tubes with diameters ranging from 2 to 3 meters. These structures are wide enough for a vehicle to drive through without touching the inner walls. It gets more complex further on. These are not simple conduits, but are engineered as underwater fortresses designed to withstand the crushing physical environment of the coastline. The equipment must resist the constant chemical corrosion caused by salt while enduring the immense pressure found at significant depths. Every section of the pipeline must survive the brute force of waves that impact the shore without interruption. The camera glides along the surface where the installation of these massive arteries unfolds like a calculated military operation. This marks the transition to the next level of hydraulic engineering. Heavy machinery positions the pipe sections with millisecond precision as the heavy steel is lowered into the surf. The construction phase concludes as the first segments are anchored to the seabed, preparing the path for the intake process to commence. 15 million liters of salt water are pulled from the ocean depths every single day through a network of specialized intake structures. Why is this massive volume of liquid diverted from the seafloor into artificial conduits? This scale of extraction is necessary to sustain the water demands of California, and the process begins with a single pipe measuring 63 centimeters in diameter. While this specific tube appears modest compared to the primary mains, it facilitates a relentless flow that defies the natural pull of the tide. Over 10,000 liters of water enter the system every 60 seconds without a single moment of interruption. Powerful pumps generate a continuous current that creates enough suction to transport the liquid from the seabed directly to the mainland facilities. One can notice the steady hum of these machines as they challenge gravity to lift the ocean into the treatment network. It only looks obvious to draw water from the source, but in reality, the composition of the raw liquid presents an immediate technical crisis for the equipment. The ocean is a living biological environment, and the intake does not consist of the purified liquid found in domestic taps. Instead, the suction draws in a dense and chaotic mixture of suspended solids and marine organisms. Thick algae, abrasive sand, jellyfish, crabs, and various species of small fish are pulled toward the intake mouths in a turbulent soup. If this unrefined mixture were allowed to reach the high-precision pumps, the internal mechanisms would suffer catastrophic failure within minutes. The equipment gradually grinds to a halt as sand erodes the impellers and biological matter clogs the intake valves. But this is just the beginning. To prevent such destruction, the engineering process initiates a brutal war of filtration and physical barriers. Hundreds of meters away from the coastline, the first defensive line is established at the very entrance of the submerged tubes. Heavy metal grates and solid screens are positioned like unblockable barriers to intercept the largest debris. It is visible how these massive screens filter out the heaviest contaminants before the liquid can penetrate deeper into the system. Everything only gets more complicated as the water moves further into the facility for more refined cleaning. 4.5 millimeters is the maximum diameter allowed for any solid object or aquatic organism to pass through the initial intake screens. Why is such a restrictive barrier necessary at the very beginning of the process? The primary filtration stage serves as a critical shield that simultaneously preserves the integrity of high-pressure machinery and protects the local marine ecosystem from being drawn into the industrial cycle. But this is just the beginning. Even after this mechanical triage, the liquid remains saturated with an invisible army of suspended sediments. Fine sand, silt, and microscopic mud particles saturate the flow, creating a murky consistency that would quickly destroy the sensitive membranes located further down the line. To neutralize this threat, the facility utilizes gravity, one of the most reliable physical forces in existence. The water is discharged into massive filtration tanks where thick, stratified layers of sand function as a multi-level natural sieve. One can notice how the water gradually percolates downward, forced by its own weight through the microscopic gaps between individual grains of silica. The dirt is trapped within the dense sand matrix, while the clarified liquid continues its descent. It only looks obvious to filter through sand, but in reality, this is a continuous and complex mechanical cycle. The equipment gradually removes the contaminated sand from the base of the tank to be washed and recirculated back into the system without stopping the flow. But the battle for absolute purity is not over yet. There are particles so small that they pass through the sand filters with ease. These microscopic entities are smaller than 1/10 of the thickness of a single human hair strand. To capture these elusive ghosts, engineering must move from mechanical filtration to the realm of chemistry. Giant mechanical mixers, resembling massive steel peacocks, rotate ceaselessly to shake the water within floating tanks. During this intense agitation, the system injects specific coagulants, such as ferric chloride, into the turbulent stream. It is visible how the visual transformation begins as the coagulant acts as a chemical magnet. The ferric chloride attracts fine dust and invisible debris, forcing the disparate particles to bind together into larger, heavier structures known as flocks. Suddenly, substances that were previously invisible to the naked eye gain mass and become visible, sinking slowly to the bottom of the tank in the form of dense mud. This leaves the water in the upper layers significantly clearer and ready for the next level of processing. Everything only gets more complicated. The system has successfully removed biological life, coarse sand, and fine dust. But the most significant adversary remains dissolved within the molecular structure of the liquid. This enemy is salt, an invisible and lethal element for both agricultural plantations and human consumption. Now the narrative enters the heart of the beast. The water is entirely free of suspended solids, but the chemical composition remains unchanged. 3.5% is the precise salt concentration held within this volume of seawater. Why must engineers deploy such immense physical force against the liquid at this stage? It would seem simple to filter a fluid, but the molecular bond between salt and water requires a mechanical intervention of extreme intensity. This energy is necessary to overcome the natural chemical attraction that keeps the brine stable. Cartridge filters serve as the final defensive line before the primary transformation begins. One can notice how the water enters these dense cylinders, which are constructed from tightly compressed fibers. These units are designed to trap any remaining particulate matter measuring between 1 and 5 microns in size. This obsession with purity ensures that no solid debris can contact or damage the most critical and expensive technology within the facility. The reverse osmosis membranes represent the point where heavy industrial engineering meets the laws of quantum physics. But this is just the beginning. Sodium and chlorine ions attach themselves to the water molecules with a fierce and relentless electrostatic force. It only looks obvious that they can be separated, but in reality, breaking this molecular bond requires immense physical power. High-power centrifugal pumps begin to rotate at high velocities, emitting a deep and constant hum that causes the concrete floor to vibrate. 60 bar of pressure is generated as the pumps force the liquid against the semi-permeable membranes. One can notice the immense energy required to maintain this flow. How can one visualize the magnitude of 60 bar? This level of force is equivalent to 60 times the pressure the atmosphere of the planet exerts on a human body at sea level. It is comparable to the weight of a full-grown elephant concentrated entirely upon a human thumb. Under this crushing mechanical load, the water molecules have no alternative but to move. The equipment gradually forces the liquid against a barrier where the pores are so small that only individual molecules of water can penetrate the surface. The process is only gaining momentum. The salt ions are larger and carry an electrical charge, which results in them being barred and physically repelled by the membrane structure. It is a molecular filter. On one side of the barrier, a highly concentrated brine remains, while on the other, drops of fresh water emerge, liberated from their salty partners by sheer mechanical strength. Almost pure is an insufficient standard for the requirements of the state of California. everything only gets more complicated. The water is directed immediately into a secondary stage of reverse osmosis to achieve the necessary refinement. This second phase utilizes membranes with even tighter tolerances to ensure the final output meets every rigorous quality parameter. The equipment continues its rhythmic cycle as the filtration process reaches its peak efficiency. The liquid passes through the final microscopic barriers, completing its transition from brine to a pure state. 444 kilometers of electrical resistance are virtually eliminated as the purification process reaches its absolute peak. Why must the liquid undergo such extreme filtration after passing through the initial membranes? The initial stages leave behind stubborn trace elements like boron and residual ions that would compromise technical specifications. Only after their total removal does the liquid transition from simple water into a permeate of absolute technical purity, possessing an electrical conductivity that measures almost zero. One can notice the liquid order emerging from the chaotic composition of the salt-heavy ocean. Millions of liters of fresh water now stand ready, but they remain at sea level along the coastline. The challenge at this stage shifts from the chemical to the geographical, as the resource must reach sedentary farms and expanding cities located hundreds of kilometers away in the interior. These destinations remain isolated behind massive, rugged mountain ranges. It is visible how the engineers must now effectively move the volume of an entire river across a continental landscape. Fortunately, the infrastructure exists in the form of the California Aqueduct, an artificial concrete artery stretching for nearly 700 kilometers. It cuts through the arid desert like a blue scar, carrying northern mountain runoff toward the parched southern regions. Connecting the desalinated seawater into this existing vascular network is the next logical step. But this is just the beginning. A titanic obstacle known as the Tehachapi Mountains stands directly in the path of the distribution route. Water does not ascend vertical inclines without external force, necessitating the intervention of the Edmonston pumping plant. This facility serves as the most powerful pumping station of its kind in the entire world. Inside, gigantic electric motors, each reaching the dimensions of a large residential house, activate to push thousands of tons of liquid upward against the pull of gravity. The equipment gradually builds the pressure required to lift the water column more than 600 meters in height during a single mechanical boost. It is equivalent to the physical work of pumping a flowing river to the top of a 150-story skyscraper. The consumption of energy for such a feat is staggering, with costs reaching into the billions of dollars over time. However, this is the calculated price of survival in an arid climate. At first glance, the energy expenditure seems immense, but in reality, it is the only way to sustain the regional economy. The resulting mixture of melted mountain snow and processed ocean water eventually begins to flow by the force of gravity alone into the Central Valley. The process is only gaining momentum as the artificial river transforms the desert into fertile land. The water moves steadily through the concrete channels toward its final destination. Thus ends the complex journey from the depths of the ocean to the heart of the agricultural valley. 800,000 acres of almond groves and vast lettuce fields across California require a constant, massive supply of water to feed the entire nation. But transporting seawater from the coast and pumping it through high mountain ranges involves astronomical costs. Why look to the distant ocean when a massive source of water flows directly beneath the city streets? At first glance, the idea of utilizing urban runoff seems impossible, but in reality, California has determined that in the struggle against drought, there is no such thing as waste, only resources that have been poorly utilized. The process is only gaining momentum. This is the transition into the world of wastewater recycling, an industrial sector where sewage is transformed into purified drinking water. It only looks obvious to discard this liquid, but it represents the final frontier of mechanical and chemical efficiency. Everything originates in the dark, sprawling sewer networks buried deep under the urban landscape. Every single household discharge, every sink drain, and every industrial stream converges to feed a toxic underground river. When this turbulent flow finally reaches the treatment station, it presents a nightmare of tangled debris, discarded paper, plastic fragments, tree branches, sand, and heavy mud. One can notice how the first stage of purification is intentionally brutal. Huge stainless steel grates intercept solid waste with mechanical force, acting as giant teeth that chew through the flow to extract rags and plastics. It gets more complex further on. The water then enters primary sedimentary tanks. Here, engineers allow the fundamental laws of physics to perform the heavy labor. The velocity of the water decelerates significantly, causing the heavy load of organic matter, food particles, and paper to sink slowly to the concrete bottom. Simultaneously, fats and oils float to the surface, where automated mechanical arms scrape them away from the liquid. Even after removing the solids, the water remains dark and saturated with dissolved contaminants. Transition to the next level. Nature is now called into the industrial fight. Inside massive aeration tanks, specialized machinery injects oxygen furiously into the liquid, creating a violent biological jacuzzi. One can notice how billions of microorganisms suddenly wake up and begin to multiply. These are the invisible workers of the recycling factory. They consume the remaining organic matter, digesting microscopic dirt that no mechanical filter could ever hope to capture. After the bacteria complete their intensive biological work, the water moves through the microfiltration stage. The equipment gradually removes the remaining suspended particles to prepare the liquid for the next chemical barrier. The process does not end at this stage, as the flow continues its journey toward total purification. 100% of pathogens are halted by the same filtration technology utilized in massive desalination plants, acting here as the definitive safety barrier. Why is such an extreme level of filtration necessary for the final stage? At first glance, the water might seem clean, but the specialized membranes are designed to obstruct microscopic viruses, bacteria, hormones, and complex pharmaceutical compounds. Not a single contaminant survives the pressure, as only the water molecule itself is small enough to navigate the semi-permeable lattice. One can notice how the liquid emerging from the rows of white pressurized tubes possesses a distinct crystalline clarity. This substance is technically classified as neophyte water. It is significantly purer than the mineral water sold in plastic bottles and carries fewer particulates than natural rainwater collected directly from the atmosphere. It stands as physical evidence that engineering can successfully strip away the chemical residues of modern civilization. Everything only gets more complicated as the process reaches a strange technical paradox. The reverse osmosis water is actually too pure for immediate distribution. Because it is completely devoid of natural minerals, the liquid becomes chemically aggressive and highly corrosive. It is visible how the lack of ions causes the water to seek equilibrium by reacting with its environment. If technicians were to pump this water directly into the municipal infrastructure, it would immediately begin to dissolve the metal lining of the city pipes. Beyond the risk of destroying the structural integrity of the network, this pure water lacks any discernible flavor. The characteristic taste usually associated with high-quality drinking water is derived entirely from mineral impurities. To correct this, the facility must intentionally reintroduce specific elements in a strictly controlled environment. The process is only gaining momentum as the flow enters the remineralization stage. Within massive stainless steel tanks, automated systems precisely dose the water with measured quantities of calcium and magnesium. This stage functions with the meticulous detail of a laboratory, where the pH level is adjusted until it becomes perfectly neutral. Achieving this chemical balance ensures the water is safe for human consumption while remaining non-reactive toward the metal and concrete of the industrial infrastructure. Huge storage tanks receive the reborn water before high-pressure pumps inject the final product into the regional municipal network. The camera glides along the massive conduits where the flow merges with the city supply. While the operational cost of this engineering feat may be 2 to 4 times higher than traditional extraction methods, it provides a permanent defense against the unpredictability of the climate. Natural reservoirs and surface lakes remain entirely dependent on the luck of seasonal rainfall and atmospheric patterns. In contrast, this industrial facility relies exclusively on the consistent application of energy and mechanical engineering. It represents a source of hydration that does not dry up regardless of environmental conditions. This concludes the primary cycle of transformation, ensuring a stable supply for the population. 625 meters is the height at which the road deck of the Huijiang Bridge suspends vehicles above the canyon floor. Why would engineers attempt to construct a massive steel structure at an altitude nearly double that of the Eiffel Tower? At first glance, such a project appears to be an act of defiance against physics. But in reality, the extreme geography of China's Guizhou province left no other choice for modern transport. The bridge, inaugurated in September 2025, now stands as the highest in the world, allowing cars to literally cross through the clouds rather than over the water surface below. The process of conquering this terrain is only gaining momentum. One can notice how the landscape of Western China is defined by a geographical nightmare of sharp mountains and high-rise plateaus. Over 92% of this specific region consists of impassable rock formations and vertical cliffs that have been 625 meters is the vertical distance that separates the planned road surface from the rushing waters of the Beipan River below. This immense height represents the core of the Liuji-Anlong Expressway project, a critical infrastructure artery designed to provide essential connectivity for long isolated communities. However, the geographic reality of the Hualiang Slide presented a technical obstacle that felt less like a construction project and more like an unrelenting confrontation with the natural world. Why did the engineers face a dilemma that seemed to have no viable solution? One can notice how the terrain dictates the limits of human ambition. A traditional route along smoother ground would have forced the bridge to sit at the very peak of the mountain range, exposing the structure to atmospheric winds of lethal velocity. The alternative only looks obvious at first glance. Lowering the height of the bridge to a more manageable level would have necessitated the construction of an extensive network of tunnels through geological formations known for extreme instability. This path would have significantly increased the probability of catastrophic landslides and structural collapses during operation. Because the safety of the future travelers was paramount, the engineers eventually committed to the supreme technical challenge. They chose to elevate the entire structure into a zone of high-altitude volatility, reaching a height of 2,050 feet. But this elevation was merely the first half of a complex mechanical puzzle. Everything only gets more complicated as the scale increases. The geography of the Hualiang Slide forms a massive V-shaped chasm that stretches over 1,400 meters between the opposing cliffs. On a scale of this magnitude, standard engineering principles and conventional bridge designs cease to be functional. It is visible how the physical limitations of materials begin to dictate the design. A rigid beam bridge of this height would inevitably succumb to its own massive weight and crumble. Similarly, even the most ambitious arch bridge design would fail to bridge the expansive void between the mountain faces. The process is only gaining momentum. Even the largest standard bridge configurations lack the structural muscle required to span such a vast atmospheric gap. Only one engineering solution remained viable for this specific set of environmental constraints. This was the implementation of an ultra-long steel and concrete strip designed to hang suspended against the sky. While the underlying theory of a suspension bridge appears simple, the execution is anything but elementary. The camera glides along the conceptual plan. The technicians must erect two massive towers, tension two primary cables, and suspend the roadway from these anchors. But in practice, the reality of working at such extreme altitudes transforms every movement into a calculated risk. Metal lays in an even layer across the blueprints, yet the physical assembly requires a mastery of tension and balance that pushes the boundaries of modern construction. 828 meters, the height of the tallest building in the world, serves as the vertical benchmark for a structure rising in a terrain that actively rejects human presence. Why must the foundation for such a bridge be integrated so deeply into the unstable Earth? Constructing a passage across the sky requires more than just height. It demands a guarantee that the bridge remains anchored to the ground against all physical forces. Before the towers could ascend, engineers faced the first deadly challenge within the foundation zone. Everything only gets more complicated as the excavation progresses. The ground in this region is not a solid mass, but rather worn rock, saturated with invisible cracks and hidden underground water. One can notice how the drilling rigs penetrate layers that appear stable but harbor structural weaknesses. A single miscalculation in this environment could cause the tower to slide into the abyss. The engineers responded with a combination of brute force and surgical precision, digging 24 shafts for solid concrete stacks deep into the belly of the Earth. These columns are reinforced with specialized steel, designed to resist high-magnitude earthquakes. They did not merely build on the rock, they effectively sewed the tower onto the mountain using these deep-seated reinforcements. But a bridge of this design lives and dies by the integrity of its anchors. It is visible how these components function like the massive muscles required to hold the tension on a titanic war cable. These anchors must withstand tens of thousands of tons of constant force, pulling the structure toward the center of the valley. On the Zhenfeng side, the technical solution relied on pure mass. Engineers constructed a gravity anchor, which is a colossal concrete block with a volume of 164,000 cubic meters. One can notice the immense scale of this single unmovable cube compacted on the back of the mountain. To understand the volume of this mass, this amount of concrete is enough to fill dozens of Olympic swimming pools. But this is just the beginning. On the opposite side, in Guanling, the geological conditions changed completely. There was a steep mountain located behind the tower site, but almost no flat terrain existed to support a giant concrete block. The space for traditional construction was non-existent. It only looks obvious to build outward, but in reality, the lack of surface area forced a change in engineering strategy. If they could not build on the mountain, they would be forced to build inside it. The process is only gaining momentum as the strategy shifts to the creation of a tunnel anchor. Engineers began the task of digging deep into the rock to create a subterranean plug. The camera glides along the dark entrance of the shafts, where the mountain itself becomes the structural support. This transition from surface mass to internal reinforcement concludes the stabilization phase of the project. The foundation is now set, allowing the transformation to move to the next phase of processing without haste. 262 meters is the height reached by the primary tower as it ascends toward the clouds. Why are these vertical structures anchored directly into the mountain skeleton rather than built on traditional foundations? At first glance, the terrain appears to be an obstacle, but in reality, engineers converted the geology into a functional ally. By fixing cables into the solid rock, they transferred the immense voltage of the system into the planet's own mass. This technical maneuver saved critical space and significantly improved the stability of the entire network. But this is just the beginning. Engineers began the ascent of these steel titans with methodical precision, raising the structures step by step. One tower reached 262 meters, while its counterpart stood at 205 meters. These are not urban office blocks shielded by city layouts. It is visible how they stand on the very edge of steep cliffs, fully exposed to powerful winds that accelerate through the natural mountain corridor. These towers serve as the pillars holding the entire weight of the world above the void. Towers of this magnitude function as the backbone of the industrial system. They must support two primary cables, each weighing more than 9,000 tons. Stability in such a configuration is not negotiable. The equipment gradually integrates high-resistance steel reinforcement into the core, designed to endure more than just the weight of heavy trucks. The material is engineered to absorb violent vibrations and seismic activity for many decades. One can notice how the structure remains motionless even when geological shifts occur. Imagine the physics of holding a steel wire in the air while an earthquake attempts to shake the supporting hands. That is the constant physical task these towers perform. Day after day, the construction of these pillars continues. The metal lays in an even layer as the assembly reaches its peak. It is visible how the cranes move with deliberate slowness to ensure every bolt is aligned. The process is only gaining momentum. From here, the transformation moves to the next phase of processing as the skeleton of the system is finalized. Everything only gets more complicated as the tension is applied to the main lines. The material is ready to move to the next processing phase without haste. 1,400 meters is the exact width of the aerial abyss that remained between the two bridge towers. The technical necessity of conquering this emptiness began with the installation of the catwalk, a temporary suspended walkway positioned hundreds of meters above the water surface. On this narrow platform, workers would eventually perform the high-risk task of cable installation. Why could traditional transport methods not be utilized to bridge this massive gap? A helicopter would be unable to maintain stability amidst the unpredictable and violent wind gusts at such an altitude, while a boat on the river below would be physically disconnected from the towers above. Modern technology provided the only viable solution in the form of high-power industrial drones. These unmanned aerial vehicles flew across the entire span while carrying the pilot line, guiding the initial wire with a degree of precision that manual human operation could not replicate. The runway for the cables took its final shape once that pilot line was securely anchored. But this is just the beginning. The process moved immediately into the construction of the main cables, which serve as the primary life support system for the entire bridge structure. Each main cable is not a single unit, but a complex assembly consisting of tens of thousands of steel wires twisted together into a massive load-bearing bundle. One can notice how the equipment pulls the material across the span with repetitive mechanical consistency. It only looks obvious to string a cable, but in reality, this is an operation of maniacal technical precision. On the suspension footbridge, workers carefully installed the cords wire by wire. Each of these individual cords consists of 91 high-resistance steel wires, each measuring exactly 5.7 millimeters in diameter. The process is only gaining momentum. Mechanical pulleys pulled these wires forward and backward between the massive anchors a total of 217 times for every single main cable. Everything only gets more complicated as the weight increases. Throughout this repetitive movement, GPS monitoring systems supervised the tension and alignment. This ensured that the positioning error remained within a microscopic tolerance, preventing any structural deviation that could compromise the bridge. The equipment gradually builds the massive steel tendons until the required density is achieved. The wire installation phase concludes with the final anchoring, ensuring the load is distributed evenly across the towers. The material is now ready to move to the next processing phase without haste. 2 millimeters is the maximum deviation allowed for the positioning of the cables throughout the entire structure. Why is such extreme precision necessary for a span stretching 1.5 kilometers? In a project of this scale, located at high altitudes and subjected to relentless mountain winds, any larger margin of error would jeopardize the structural integrity of the entire crossing. But this is just the beginning. A specialized compacting machine moved along the length of the main cable to compress thousands of individual wires. It is visible how the equipment exerts immense pressure to squeeze the bundle into a dense, perfectly circular cylinder. Layers of specialized protection were then applied to the exterior of the steel to shield the metal from corrosion and extreme weather conditions. Only when these two massive steel arteries, each weighing 9,000 tons, were fully secured and reinforced, could the project transition to the next level. The heavy lifting phase began with the installation of the road deck where vehicles will eventually travel. First, engineers lowered vertical suspension bars and attached them firmly to the main overhead cables. It only looks obvious to hang a road from above, but in reality, the boardwalk was not constructed on site. 93 individual steel segments were manufactured separately to be assembled like a giant airborne puzzle. Each of these segments weighs several hundred tons and had to be transported one by one from the center of the deep valley. One can notice the slow movement of the cranes as they hoist these colossal weights to a height exceeding 600 meters. The process is only gaining momentum. Gravity and high-velocity winds constantly fought against the stability of each piece during the ascent. Engineers were forced to monitor and adjust the cable tension without interruption to prevent the bridge deck from leaning or twisting out of alignment. This dangerous industrial ballet required 1,000-ton components to be positioned with centimeter-level accuracy while suspended in the void. Everything only gets more complicated as the focus shifts to the materials used for the foundations. 439,000 cubic meters of concrete were required to complete the massive Huajiang Bridge. To visualize the scale of this volume, one can imagine 176 Olympic-sized swimming pools filled to the very brink with liquid stone. It seems simple to just pour massive amounts of resources into the pylons, but the engineers chose a more efficient technical path. They collected the residual rock excavated from the surrounding mountains, which would normally be treated as industrial waste. The equipment gradually crushed this stone into a high-performance green mineral powder. By introducing this recycled material into the mixture, the team successfully replaced 20% of the cement required for every cubic meter of the structure. The mineral powder enhances the chemical properties of the concrete while reducing the environmental footprint of the massive construction. The transition to sustainable materials allowed the project to continue its expansion without a massive increase in external supply chains. The bridge deck slowly reached its final configuration high above the canyon floor. From here begins a new stage that will finally shape the rail and road surfaces for future use. 3,700 tons is the total weight of the mechanical force that concentrated on the bridge deck during the final phase of testing. This strategic utilization of recycled materials did not merely reduce financial expenditures by significant margins, but also ensured the protection of the surrounding ecosystem by converting industrial waste into structural reinforcement. Why was such a high-intensity approach chosen for the final verification? It would seem that digital simulations or smaller weights could provide sufficient data for the engineers. But mathematical models cannot fully replicate the physical reality of a finished structure, requiring a demonstration of brute force to confirm absolute stability. The steel reinforcement shone under the direct sunlight as the concrete reached its full curing maturity, signaling the completion of the construction cycle. It is visible how the gray surfaces of the massive piers stand ready to support the upcoming pressure. Transition to the next level. In August of the year 2025, the engineering team initiated the definitive load test to verify the integrity of the entire span. They did not rely on sandbags or static computer predictions to finalize the results. Instead, 96 heavy trucks, each loaded to its maximum capacity, began their synchronized movement toward the center of the bridge. The engines rumbled in a steady sequence while the heavy tires pressed firmly into the fresh layer of asphalt. One can notice how the immense weight causes a slight compression of the suspension systems as the vehicles align across the lanes. Over 400 sensors distributed across the entirety of the bridge monitored every physical change within the structure. These precision instruments measured the deformation of the spans, the frequency of the vibrations, and the exact tension within the support cables. It only looks obvious to drive vehicles across a flat surface, but in reality, every millimeter of movement was tracked in real time. If the bridge shifted even a single centimeter beyond the calculated parameters, the entire project would be classified as a technical failure. The structure remained firm under the 3,700 tons of steel and cargo. The process is only gaining momentum. This successful test confirmed not only the safety of the bridge, but also the extreme precision of the calculations established years prior to the first stone being laid. Everything only gets more complicated when considering the natural environment surrounding the site. The challenges faced by the human technical team were characterized by brutal environmental conditions. The Huajiang Canyon functions as a natural wind tunnel where air currents are compressed and accelerated by the rock walls. One can notice the sheer force of the wind as it strikes the cables and pillars. It is documented that the wind speeds in this specific gorge can reach level 14 on the Beaufort scale, equivalent to the force of a hurricane. The material remains in its final tested state, having proven its ability to withstand both gravitational loads and the relentless pressure of the atmosphere. The structure is now fully verified and ready to enter its operational lifespan. 625 meters is the height at which the final stage of the high-altitude construction was completed under extreme conditions. Laborers continued their work until the onset of total darkness, manually straightening thick steel cables while enduring the abrasive force of the mountain winds. At first glance, this effort appeared to be a struggle against the raw fury of the natural elements. Why did these teams persist through such physical exhaustion and environmental resistance? Manual labor was the only way to ensure the precise alignment of the structural components that machinery could not calibrate in the thinning atmosphere. This human persistence eventually overcame the geographical barriers that had isolated the region for centuries. The transition to the next level of regional connectivity is now a physical reality. Where an unobstructed mountain barrier once forced travelers into 3 hours of dangerous transit along winding roads, a straight asphalt line now exists. One can notice how the travel time has been reduced to exactly 1 hour and a half. The bridge successfully connected the G56 expressway, which functions as a vital commercial artery between China and the Southeast Asian markets. But this is just the beginning. The infrastructure immediately triggered an influx of tourism and professional opportunities into a territory previously characterized by its total isolation from modern trade. It is visible how the structure integrates into the landscape when returning to the observation point positioned at an elevation of 625 meters. At this height, the river below appears as a thin silver wire more than half a kilometer away from the transparent glass floor. It seems simple to stand above the clouds, but in reality, Every square inch of the view is supported by massive industrial output. The Beipanjiang Bridge consists of more than 439,000 cubic meters of high-strength concrete and 9,000 tons of specialized steel cables. The process is only gaining momentum as these materials maintain the tension required to span the abyss. Everything only gets more complicated when calculating the engineering precision required to transform immortal chasm into a stable transport corridor. The project moved from the initial chaos of controlled explosions to the final laying of smooth asphalt across the deck. Engineering ambition converted the unpredictable nature of the mountain range into a disciplined and perfect line of industrial order. This transition from raw geological matter to a functioning bridge marks the completion of the structural narrative. The material has been successfully integrated into the international transport network, and the transition to a new era of regional commerce is now complete. Thus ends one of the most challenging chapters in modern bridge construction. 1,100,000 square kilometers of forest, exactly 1/5 of the total Amazon rainforest, is the scale of the green expanse that vanishes from the planet every single year. This monumental loss of vegetation serves a singular industrial purpose: the production of 80 billion rolls of toilet paper consumed by humanity over the course of 12 months. 15 million hectares of trees are sacrificed annually to meet this global demand for hygiene. Why should such an immense ecological price be paid for a disposable commodity? It seems logical that a more sustainable source of fiber exists within the very waste streams humanity generates daily. Everything only gets more complicated when considering the engineering required to convert contaminated refuse into a sanitary product. One can notice the heavy movement of diesel engines as the process begins at the industrial courtyard. Collecting trucks, acting as massive steel transporters, arrive at the facility to discharge what appears to be a chaotic mass of urban debris. These vehicles dump 500 tons of waste every 24 hours onto the reinforced concrete floors. At first glance, the pile is a disorganized mixture of discarded materials, but in reality, it contains the essential raw materials for the entire plant. Plastics, metals, organic food scraps, and glass fragments are intertwined with various grades of paper within the heap. The atmosphere is thick with a heavy industrial scent, while the visual landscape remains cluttered and gray. For the engineering systems of this facility, however, this mass is not viewed as garbage, but as high-value raw material. The initial stage of the transformation is a concentrated effort to eliminate contamination from the fiber stream. The unsorted material is pushed onto gigantic conveyor belts that flow like continuous rivers of rubber and steel through the sorting hall. Here, the technology must operate at a tempo that exceeds the capabilities of the human eye. Advanced optical sensors are positioned above the belts to scan every fragment that passes at high speed. It is visible how these sensors identify the chemical signatures of different materials that are invisible to the naked observer. When a plastic bag, a strip of nylon, or a non-paper intruder is detected, the system reacts with millisecond precision. Compressed air jets act as invisible projectiles, firing with a sharp hiss to eject the contaminants from the production line in fractions of a second. This mechanical sorting ensures that only the fiber remains for the next stage of processing. But the technology does not function in complete isolation from human oversight. In many facilities, specialized workers are positioned along the lines to provide a final layer of manual verification. These operators are equipped with heavy protective gear, including industrial masks and thick rubber gloves, to navigate the harsh environment of the sorting floor. The process is only gaining momentum as the purified paper moves toward the massive pulping units. From here, the transformation moves to the next phase of processing. 8 specialists, dressed in heavy industrial gear and thick security glasses, perform the final triage. Their gloved hands move with precision to manually extract any remaining contaminants that automated sensors might have overlooked during the previous sorting stages. This human intervention is a rigorous requirement to ensure that only the purest paper fibers remain on the moving line. But this is just the beginning. Why is human oversight still necessary in an age of automation? Automated machines are efficient, but certain flexible plastics or small metal fragments can mimic the physical properties of paper. The final manual check prevents these foreign objects from entering the delicate chemical phases of the recycling cycle. Colossal vibratory separators receive the material next, shaking the entire floor with the concentrated force of a controlled earthquake. One can notice how the equipment gradually oscillates on heavy-duty springs to isolate different material densities. The physics governing this stage is simple and brutal. Vibration causes heavy, undesirable materials to sink and fall through designated traps, while the lighter paper fibers continue to flow forward toward the next processing step. It seems simple to just shake the material, but in reality, the frequency must be perfectly tuned to avoid losing valuable fiber along with the waste. Hydraulic presses then receive the cleaned material to create recovered paper rugs. These machines exert 1,000 kilograms of force, compacting the loose fibers into dense, square blocks that resemble giant industrial bricks. 800 kilograms is the exact weight of each individual rug emerging from the press. And this is not the limit. It is visible how the metal plates of the press retract with a hiss of hydraulics, leaving behind a solid mass of concentrated fiber. Think about the potential contained within a single one of these 800-kilogram units. One solitary block provides enough raw material to manufacture more than 10,000 rolls of new toilet paper. What was once a discarded pile of waste on a city sidewalk has been transformed into a cube of concentrated potential. Everything only gets more complicated as the material prepares to be dissolved and reborn. The process is only gaining momentum as stackers transport the paper rugs and deposit them into a hydropulper. One can notice the machine resembles a liquidifier the size of a two-story house. The primary tank is flooded with a precise volume of water, maintaining a rigorous technical proportion of 10 parts of liquid for every 1 part of paper. At the bottom of this massive industrial vessel, a monstrous steel rotor begins its work. The equipment rotates at an incredible speed, between 1,000 and 1,500 rotations per minute. The energy is very high, as the mechanical force begins to break down the physical bonds of the compacted blocks. It only looks obvious that water would soften the paper, but in reality, the high-speed vortex is what effectively separates the fibers into a workable slurry. Transition to the next level. The solid blocks vanish into the swirling gray liquid, signaling the completion of the primary preparation phase. 100% of the recycled material undergoes a violent physical transformation within the pulper. The water turns into a furious vortex that attacks the paper, tearing it not into pieces, but into microscopic fibers. Why is such intense mechanical agitation necessary for the raw material? It seems like a simple soaking process, but in reality, this is where the dirt from the past is erased. Special chemical products, known as dispersing agents, enter the mixture to hunt for the prints and old glue. The process lasts between 30 and 60 minutes of implacable agitation. One can notice how the ink comes off the fibers and flows to the surface or dissolves entirely. This leaves behind only the pure cellulose. The result is a gray paste, a soup of suspended fiber in water. But this soup is not yet paper. It passes through fine dyes that capture even the smallest particle of plastic or the grass that has survived so far. The process is only gaining momentum. Now a clean pulp exists, but it consists of 95% water. To make the soft product we know, it needs to undergo a radical physical transformation. Free fibers begin to look for each other, creating natural hydrogen bonds that will form the dorsal spine of the new paper. It is biology and chemistry working together under the command of heavy engineering. Liquid pulp is pumped into the formation machine, which functions as the heartbeat of the factory. Here, speed is everything. The mixture is spread over a thin mesh screen, which moves so fast that it is visible only as a metallic blur. The water needs to be removed, and the equipment accomplishes this with extreme velocity. Rotating cylinders and vacuum systems suck the moisture with tremendous force. Gravity and suction work together to drain the water, leaving behind a wet fiber cloth. But the leaf is still fragile. It enters the press area, where giant steel rolls crush the newborn paper. It gets more complex further on. The pressure is calibrated with millimetric precision. The goal is not just to dry the material, but to define the thickness of the sheet. One can notice how the moisture is squeezed out as the rollers rotate ceaselessly. We are talking about a precision that is as sharp as possible. The final sheet will have a thickness of between 15 and 20 microns. The material is ready to move to the next processing phase without haste. 1/100th of a millimeter is the thickness of this fiber layer. making it significantly finer than a single human hair or a floating dust particle. This delicate web of material adheres to the surface of a massive steam-heated drying cylinder known in the industry as a Yankee dryer. Why is the thermal application so aggressive at this specific point? The heat must be intense enough to evaporate every remaining molecule of water in a fraction of a second. This thermal shock transforms the substance from a saturated gray liquid into a dry, continuous white sheet of paper in an instant. The process is only gaining momentum. One can notice how the paper flies through the internal mechanisms of the machine at high velocity. It passes through a series of precision rolling pinwheels that polish the structural surface of the sheet. This mechanical friction creates the specific soft texture that is mandatory for consumer requirements. At the end of this automated line, the material is wound into jumbo coils that defy standard proportions. These are not common rolls found in a household. Each unit exceeds 1 meter in diameter and possesses a mass weighing several tons. Inside each coil, kilometers of continuous paper are stored in a massive reserve, awaiting the high-speed cutting phase. It only looks obvious that the material is finished, but in reality, this is merely a bulk storage state. It is an impressive scale of production where a single coil of this magnitude contains enough material to supply the needs of an entire family for a lifetime. Everything only gets more complicated. The paper itself possesses no structural rigidity and cannot maintain a shape on its own. It requires an internal skeleton to provide support for the layers. While the paper formation concludes on one side of the facility, the cardboard tube is simultaneously manufactured at the opposite end of the factory. It seems simple, almost like a minor technical detail. But without this core, the final toilet paper roll would collapse under its own weight during the winding process. One can notice how recycled cardboard strips are fed into a spiral wrapping machine with synchronized timing. This is a highly precise mechanical operation where the strips are bathed in a specialized ultra-fast drying adhesive. The equipment then wraps the saturated cardboard around a solid steel axis to create the cylinder. The geometry here is fundamentally simple, yet it provides the necessary foundation for the entire product structure.